Okay, so in chapter 20, we're continuing our look at sound, and we will be looking at the origin of sound, the nature of sound, and the speed of sound in part 1. So let's go look. So again, sound, like vibration, is caused by a disturbance, usually the vibration of material objects that send a wave of disturbance through the air. So when you pluck a guitar string, it vibrates the sound box of the guitar. This is an acoustic guitar, of course. And so then what happens is the sound box is vibrating, and that sends waves out into the air. So a guitar string alone does not send out enough sound. So it helps to have the sound box. So the string does send out a little bit, but not much. So you can see some drum heads down below. And of course, we've talked a little bit before about how frequency is related to pitch, and also how frequency relates to wavelength. So remember, as frequency increases, then the wavelength decreases if the waves are moving at the same velocity, which often means under the same tension. Now, for the drums over here, the wavelength relates to the size of the drum head. And so when you have a larger drum head, basically the drum head plays in its fundamental. It just goes up and down. And so you can see how that, of course, is going to make a wavelength that's twice the size of the drum head. And so, of course, you're going to expect to hear a lower pitch from the bigger drum head and a high frequency or high pitch from the small one. Oops, that's supposed to be an H. So high pitch. And so as an example of that, I've got a drum over here, which is a Irish drum. It's called a bodhrán. And you can hear it has a very deep sound. And as I hit it, of course, that makes this goat skin or cow skin, get which one, vibrate. Now, because the speed depends on the tension, and that's going to change the sound if I change the tension. So the bodhrán is played by pushing on the back of the drum to change the tension. Because essentially what I've done here is made it by pushing on it, I've made it higher tension. And I'm getting some echo effect here too from the drum head, because as I speak, it echoes and vibrates with my voice. Anyway, so you can have all sorts of fun with a bodhrán. Sorry, it's from my Irish band days. Okay, so anyway, so yes, drums can be a lot of fun. And where you play on a drum can count too, because if you're close to an edge, then what can happen is that if you play on the edge of a drum, so closer to one edge rather than just in the center, you can make a smaller wavelength, basically, as it reflects off that part, and a longer one over on this side. So you can adjust the sound by moving where you're tapping the drum. So anyway, so drums are fun. Okay, so the nature of sound has to do with a pressure wave, as we mentioned before. And what's getting pressurized is the air molecules. So if you imagine this all starting with air molecules that are equally spaced, as the wave moves through, the molecules will be pushed into areas of compression and away from other areas that we call rarefactions, because it's rare to find molecules there. So anyway, so the molecules move back and forth as the wave passes, and those compressed areas move along till that sound reaches your ear. So compressions and rarefactions. Okay, so you can compress air in a room if you've ever gone into a room and swung the door open and the curtain flies towards the screen. Or the other way, you can take some air out with you, producing a rarefied atmosphere. And again, note, the air molecules don't travel from the source to the observer. So the air molecules here are not reaching your ear. So that's kind of nasty if the molecules as I speak are the ones that reach your ear. But no, what happens is that compression wave moves through and compresses molecules along the way. And that occurs because our tuning fork here is, of course, pushing outward, vibrating outward, pushing on the molecules. Then it pulls back in, then it pushes out again, sending pulse after pulse of compression through the air. Now, our ear is going to hear that. And this picture is not from your book. What's going to happen is those waves are coming in, those waves of compression, and they hit the eardrum, which is a very delicate little flap of skin, which is why you're not supposed to poke things onto your eardrum. And that little flap of skin is connected to three little bones called the malleus, the incus, and the stapes, or the hammer, the anvil, and the stirrup. And what happens is at the end of the stirrup, the pulse of sound, the pressure wave, has been magnified about 4 times, because basically this is a little lever system. And that pushes on another drum head, which is part of the cochlea. And the cochlea is the part that detects sound and sends the signal to your brain. So let's go look more at the cochlea and what it can hear. Basically, humans can hear a range of hearing from 20 to 20,000 hertz. So that little tiny eardrum is vibrating maybe up to 20,000 times per second. As you get older, like me, you start to lose hearing. So a lot of people your age can only hear up to 17 or 18,000. Okay, because only babies usually can hear 20. A few students I've tested hearing over the years. Unfortunately, it doesn't work well through a microphone because it depends on my microphone, your speaker system, and the signal in between. So it doesn't work well. I can't do a hearing test for you, sorry. But you can do one of your own because you can get a frequency device on your phone, and you can use that to test your own hearing. So anyway, so yeah, there are apps you can get. We'll look at one later. So humans can hear from 20 hertz to 20,000 hertz when they're born, supposedly. As they get older, they start to lose it. By the time they're my age, I can only hear up to about 12,000 hertz, which is a shame. Okay, so I cannot hear sounds over that. So sometimes people have been known to set their cell phone rings to a frequency higher than their teacher can hear, which just irritates other students, though, so don't do it. That's a nasty sound. Okay, so anyway, but I can hear it. Ultrasonic frequencies are greater than humans can hear, so that's about 20,000 hertz. And infrasonic frequencies are frequencies smaller than humans can hear. Now, which is around 20 hertz. Now, I've been having students test their hearing, and they can often hear down to 10 hertz or lower. So 20 is kind of an approximation. Probably it sounded good to say 20 to 20,000 for one thing. But yeah, I think people can hear lower, but usually they have to have the speaker close to their ear. If it's a meter away, they might not be able to hear it. So maybe this is defined for 1 meter away. Anyway, of course, some animals can hear, like dogs and cats and dolphins. They use ultrasonic frequencies. And so anyway, so you hear about dolphins detecting fish and stuff using ultrasonic frequencies. Infrasonic frequencies, about the only animals that use those are elephants. Elephants can actually produce infrasonic frequencies. People feel them as a rumble in the ground, but it's elephants talking to each other over great distances, saying, "Here I am. Come mate with me." Okay, so usually it's the males sending out these low rumbling sounds. Okay. So the cochlea is a fascinating thing. What happens is each spot along this double coil of tubing can detect a different frequency. What happens is that it's full of a fluid, so it's fluid filled, and the fluid will vibrate in certain places depending on the frequency that's coming in. It resonates. And so when you hear 7,000 hertz, it resonates here. When you hear 4,000, it resonates here. If you're hearing 1,000, it resonates here. And one of the cool things about this, of course, is you can hear all those sounds at the same time. So humans enjoy the pleasure of of chords, right? Like on a guitar, you have different notes that you're enjoying at the same time. And so it's really great function of our hearing. Now, what's happening is there are these little hairs inside here, and they have to dance together. So when there's a resonance here, the fluid sloshes around, makes the little hairs dance or vibrate in place. Those little hairs are joined together by a tinier little hair called a tip link. And that keeps them bundled together because you want them working together. And that sends a signal to your brain when those little hairs vibrate together. They send a strong signal to your brain. Anyway, so when you hear a sound that's too loud, and sometimes people have temporary deafness, what happens is that you can shake your hairs apart. They break the tip link and stuff. And so that has to grow back, which you can do quickly so that you can regain your hearing. Now, sometimes you damage things so badly that either you can, what can be damaged is the little bones, the incus, the stapes, and the malleus, or you can damage the eardrum itself, or the little hairs in here can get damaged. As we get older, one of the reasons we stop hearing higher frequencies is that you start to lose these high frequencies here. But sometimes we just listen to a machine that's going the same frequency over and over and over again. We lose our hairs at that location. So that's why you're supposed to wear ear protection if you're using machinery, because it gives the same. So like if you were listening to 1,000 hertz on, a machine that you were using at work, wear your ear protection, because what it does is it kills the little hairs through overuse, and then they fall out. And you're bald inside. You may look good on top, but inside you're bald. So anyway, so wear ear protection. And a lot of musicians are deaf because they have loud speakers close to them. Okay, so anyway, so keep your hearing. Don't be deaf. Ultrasonic, of course, can be very useful for because they can get inside our skin and they can reflect off items. So they're used as a substitute for X-rays. So for babies, you don't want to harm the baby, so ultrasonic works great. Gallstones, appendicitis, that sort of thing can be detected with ultrasound instead of X-rays. Now, dolphins, as I said, do use ultrasonic signals. We'll talk a little bit about that later. But dolphins, of course, also use sonic. Sonic would be in the range of human hearing. So when you hear a dolphin go, like Flipper, that is a sonic sound. And humans can't hear their ultrasonic signals. Okay, what's the speed of sound? Well, sound in dry air moves at around 340 meters per second when the temperature is about 20 degrees Celsius. If it's 0 degrees Celsius, so freezing, then it's about 331. Sound moves at different speeds in different materials. So it's fast through solids where the molecules are next to each other, linked to each other. and then liquids, and then it's slowest through air. And sound cannot travel through a vacuum. So there's a formula that you need for the lab and the test, maybe a homework. Anyway, the velocity of sound is 331.5 plus 0.6 times the temperature in degrees Celsius. And in general, in water, it's about 4 to 5 times faster than in air. In steel, it can be 10 to 15 times the speed in air. The first test for the speed of sound was in 1826. So the speed of sound in water. And so somebody rang a bell on one boat, and somebody was listening to it at another boat. Okay, so what's the velocity of sound at 28 degrees Celsius? Well, velocity would be 331.5. That was the velocity in dry air at 0 degrees Celsius. And then for every degree that it goes up, it's 0.6 meters per second. So then we would just multiply by 28 degrees. And we would end up with 0.6 times 28. And so that's 16.8. And we would end up with 348.3 or so meters per second. Okay, so I'm not sure that equation is on your equation sheet. So that's another one you might want to write down so you have it handy. You do use it in the lab. And here are some speeds of sound in different materials and some at different temperatures. And notice the speed in helium is much higher than the speed in air. That's why when you suck on a helium balloon and you've got that in your lungs and then you try to talk, that makes that squeaky sound because of the higher velocity, which goes to a higher frequency of sound. Anyway, so you can see how in these liquids, it's traveling about in the 1400s, from 1,000 to 1,500 meters per second. For solids, you can see it's traveling from around 2,000 to 6,000 meters per second. So much faster in solids than liquids, much faster in liquids than gases. And that's the end of that section. So I'll see you for part 2.